This is problem 539. Steady flow adiabatic turbine or expander accepts gas at conditions T1 and P1, discharges at T2, P2. Assuming ideal gases, determine per mole of gas the real work, the ideal work, the lost work, and the entropy generation, total entropy generation for the following case. Take T surroundings of 300 Kelvin. So we've got a little turbine here. T1, 500 Kelvin, P1, 6 bar, T2, 371 Kelvin, P2, 1.2 bar. We are told that the heat capacity CP is 7/2 R, and so you should know that means that CV is CP minus R, so that is 5/2 R. We're told it is adiabatic. That means there's no heat transfer. Q dot is equal to 0. This is a perfectly insulated turbine, no heat losses. It is also producing work. All right, so this is also steady state, so steady flow. We already wrote down that it's adiabatic, well insulated. Also changes in kinetic energy and potential energy, we're going to neglect those. And what do we want to find? We want to find the work. I like writing real work, ideal work, lost work, and the total entropy generation, S dot gen or SG. All right, so I think we got our schematic, we've got our given information, properties, some assumptions, what we want to find. A lot of times in these work problems where we have ideal and real work, we're given a thermodynamic efficiency. Do we have that? No, we don't. We don't have a thermodynamic efficiency. What that means is that we should be able to calculate these things. We should be able to calculate the real work right off the bat. So let's take a look at that. Can we calculate the real work right away? How do we calculate the real work? Well, that comes from the first law, right, for an open system. And it's steady state. So remember, we have accumulation is equal to the input. So I'll write m dot in times Hn minus the output, m dot out times H out, right, plus Q dot plus W dot, where this is the real work, right? Because this is our real system. We can simplify this. We know that this is equal to 0, and so we can rearrange this to say the real work is equal to m dot times delta H, right? M dot times delta H. That's our energy balance for an open system. If this were steam, we could look up the enthalpy of the inlet and the outlet and get our work calculation, but this is not steam. This is an ideal gas. What is the enthalpy change for an ideal gas in an open system? Well, the answer is it doesn't matter what kind of system we're dealing with. The enthalpy change for an ideal gas undergoing any process is the integral of Cp dt from T1 to T2. And since heat capacity is constant, we can pull that out. The real work for this process is equal to m dot times C sub p times T2 minus T1, right? We don't know m dot, so we're just going to keep everything on a per mole basis. We can divide through, you can think of dividing through by m dot but I'm just going to leave it like this. So this is 7/2 times 8.314 joules per mole Kelvin times 371 Kelvin minus 500 Kelvin. Right? Units, Kelvins cancel out. I'm left with joules per mole. The real work is equal to minus 3783 joules per mole. Does that make sense? Well, we look at the sign. The sign's negative. That should be negative, right? It should be negative because our system is doing work on the surroundings. So energy is leaving in the form of work. We should have a negative work. So as far as we know, that looks like it's correct. All right. Now, the next thing we're asked to calculate is the ideal work. So the ideal work, we're given this. You can calculate this based on information in your textbook. We don't have to go through and rederive it. The ideal work is equal to delta H minus T surroundings times delta S, where this is delta S of our system. So delta H, we actually already calculated it. It's just the work, right? We know T surroundings. T surroundings, I didn't write that down. That's 300 Kelvin. What about delta S? Do we know delta S? Well, we were given the equation for delta S in our textbook for an ideal gas in a closed system undergoing a reversible change. That delta S is equal to Cp, natural log of T2 over T1 minus R, natural log of P2 over P1. So I've written that down, but right before I wrote it down, I said that this equation was derived for an ideal gas undergoing a mechanically reversible process in a closed system. Here we have an ideal gas going through a real process, and it's certainly not reversible. So the question is, does this formula still apply? And the answer is yes. This formula still applies because everything in here is a state function and it's path independent. All we care about for calculating delta S is the initial state and the final state. It doesn't matter which path it goes through. The delta S is going to be the same no matter what. So we can plug our values in. We already know everything, right? So that's 7/2 times 8.314 joules per mole Kelvin times natural log, this is 371 Kelvin over 500 Kelvin minus 8.314 joules per mole Kelvin times natural log of P2, which is 1.2 bar, over P1, which is 6 bar. All right, and no units in the log operators. Those are all going to cancel. Joules per mole Kelvin, joules per mole Kelvin. That's what we need for delta S. We do that calculation, and we get, punch those numbers in, 4.698 joules per mole Kelvin. So, important intermediate. Now we have everything that we need to calculate the ideal work. And so we can plug those numbers in. The ideal work is equal to minus 5192.4 joules per mole. Again, let's see if that makes sense. Number one, it's a negative sign, which it should be because our system is doing work on the surroundings. What about comparing the ideal to the real work? Should this number be lower or higher? Well, on an absolute sense, it should be higher, but when we take into account the signs, of course, it should be more negative. The ideal process without any irreversibilities, right, any friction or anything like that, should produce a lot more work than the real process, which has friction and all sorts of other irreversibilities in it. So these two numbers, while we just have to trust our math to make sure the absolute the numbers themselves are right, but the trend is correct. So that gives us a little bit of confidence as we go through this problem. Now the next thing we're asked to calculate is a lost work. Calculating the lost work. So probably the easiest way to think about the lost work. The lost work is equal to the real work minus the ideal work. We've already calculated those, so all I have to do is plug those in. So the real work minus 3783 joules per mole minus the ideal work minus a negative 5192.4 joules per mole. So just make sure you keep your signs right. That's the most common mistake, is just someone forgets that this is a negative work. So the lost work, it becomes 5192 minus 3783. The lost work ends up being 1409. And you can have the 0.4 joules per mole. And that makes sense. We're losing a positive amount of work. All right. There's also another way you can do the lost work. All right. This equation is actually, it was equation 525. And we used it because we had just calculated these values. We could have also used equation 527. All right, equation 527 says the lost work is equal to T surroundings times delta of m dot times S of your streams minus Q dot. All right. So we know Q dot, that's equal to 0. And so we could plug this in. This would be T surroundings. Is what? That's 300 Kelvin. And what is our delta S? Our delta S is 4.698 joules per mole Kelvin. All right. If I take 300, 4.698, I get the same answer. All right. And then what else do we need to calculate? We need to calculate S dot generation. We need to calculate the total entropy generation. And so from there, what we can do is we can go to our entropy balance. And remember, this is a little different from an energy balance because entropy is not conserved, but this is equation 5.16. Equation 5.16. And so our entropy generation, so our entropy generation says that S dot gen is equal to what? The accumulation term for our control volume, that's equal to 0, plus m dot delta S. This is our input and output, which we just calculated right there, right? And then what else? We have our entropy generation from our entropy change for the surroundings. So that is minus the sum of Q dot J over T surroundings. Right, there's a summation. So that is our, and of course that has to be greater than or equal to 0 to satisfy the second law. So what do we do here? Well, we were given a T surroundings here. Do we need to calculate, is there an entropy change due to the surroundings? We're given a T surroundings, but remember the heat transfer, there's no heat transfer between our system and our surroundings. So there's no delta S for our surroundings. Everything is due, S dot gen is due to our system, right? It's due to our system. So that's delta S of our system in this case, which we just calculated at 4.698 joules per mole Kelvin, right? So that is our entropy generation, and look, that is greater than or equal to 0, so the second law is validated. Now the question is, what if I had given you a Q? What if I had given you a Q, and this would have been a heat rejected to the surroundings because it has to go from hot to cold. So if I had given you a Q, that would have affected this calculation here, right? That would have affected your work calculation. Would it have affected this at all? It wouldn't have affected the ideal calculation. Would it have affected the lost work calculation? Yes, it would have affected the lost work calculation, and you would have included that in your entropy generation term. But here the problem was a little simpler. No heat transfer makes things simpler, and so our total entropy generation is just, in this case, the total entropy change of our system.